Well, it's a pleasure to be here. This is in memory of Stephen Hawking, 8th January 42 to 14th March 2018. Now, I did my BSc Honours here in the Physics Department, which was then in what is now the Mathematics Department before this building existed. I then went to Cambridge to the Applied Mathematics Department, which was in something called the Phoenix Wing in the Cavendish Laboratory in Free School Lane. Now, it was called the Phoenix Wing because the physicists who had inhabited had burnt it down, and it was then rebuilt, and that's why it was called the Phoenix Wing. So it was taken over by the Department of Applied Maths and Theoretical Physics. There were some major names there at that time. Fred Hoyle was there as a gravitational physicist. Paul Dirac was there. And the head of the department was George Batchelor, a fluids dynamics person. So I went to lectures by Fred Hoyle and by Paul Dirac, amongst other people. My research supervisor was Dennis Sciama, who is a name that may not mean a great deal to you, but he was one of the great research supervisors in general relativity and cosmology theory. This is the entrance to the Cavendish Lab Free School Lane, so I used to go up there through that entrance every day and then up a whole series of steps to the Phoenix Wing, which is right up at the top. And that's a picture of Dennis Sciama, who had many, many very famous research students, because he was a genius at supervising in these areas, general relativity, cosmology, and astrophysics. Now, Stephen Hawking came from Oxford to Cambridge in 1962. Now, he wanted to have as his supervisor Fred Hoyle, who was very famous at that time because of many books, radio appearances, and so on. However, Hoyle was not willing to take him on as a research student, and so he was assigned Dennis Sciama. He was a bit disappointed about that to begin with, but then became very, very grateful because Dennis, as I've said, was an extremely good research supervisor. He started off up at the Phoenix Wing, and there was a lot of stairs to go up. And when he started coming up there, we gradually saw him having more trouble going up those stairs, because this was the days when his disease was beginning to affect him. There was another South African up there at the top, Jerry Lemmer, that some of you may remember, perhaps of the older ones of you, who came back and was at UNISA for very many years. Now, we moved from the Phoenix Wing to Silver Street, the old Cambridge University Press site, and there I was there together with Stephen for many years. Initially, we had separate offices on the top level of that building, and then later we shared office down at the ground floor. Another very, very good relativist there was Brandon Carter, who was very well known in terms of black hole physics. And Martin Rees was another research student who is a very, very famous astrophysicist, president of the Royal Society, astronomer royal, president master of Trinity College, Cambridge, and so on. So he was one of the very distinguished students later on in his life, who was one of our colleagues there as a student. Now, where Stephen cut his teeth, as it were, was that at the time, Fred Hoyle and Jen Narlikar, an Indian student of his, were working on an action at a distance theory of gravity. One of the most strangest things about gravity is that the moon over there can cause tidal forces over here. Now, how does that happen? And when Newton did his theory of gravity, he didn't say how it happened, he just described it by an equation. Einstein tried to describe it by a field theory. There's a gravitational field which propagates from there to over here. Hoyle and Narlikar tried to say maybe you can go back to Newton and say action takes place at a distance without an intervening field, and they developed a very interesting theory which looked at that. And they published that, and then there was a Royal Society meeting where this was discussed. And Stephen was told by Dennis Sciama to look at this theory and examine it, and he found out that actually there was a problem with the theory. So at this Royal Society meeting, which is an extremely distinguished meeting, Fred Hoyle gave a presentation of this with Narlikar there as his support, and then Stephen, who was just a graduate student, stood up there and said, "Professor Hoyle, you're wrong." And Hoyle said to him, "How do you know it's wrong?" And Stephen said, "I have calculated it." And the integral diverges. And so this already showed the kind of initiative and power of Stephen's thing, that he was willing as a graduate research student to stand up to one of the most famous research professors in astrophysics at that time. And he published that as a paper in the Proceedings of the Royal Society of London in 1965. Now, he got married to Jane Wilde in 16th July 1965. That's a copy of the invitation that my wife and I got from them. And that's a picture of Stephen, and you can see he's already having to use a stick to hold on, because his ability to walk was already a little bit down, but he certainly wasn't in a wheelchair or anything like that. So that was his wedding on 15th of July 1965. And this is his family life now. He had a little house in Little St Mary's Lane, just the way round from the Free School Lane building, and that's the picture on the left. And that's a picture of him on his right with his son Timothy and his daughter Lucy and his wife Jane. In those Cambridge days, I used to go around often with him to Little St Mary's Lane. It had many, many stairs. Those British houses are very, very narrow, and they go way, way up. And Stephen started having more and more trouble going up those stairs as his disease progressed, and he used to have to go a few stairs at the time, take a rest and go a few stairs and so on. I remember one particular day sitting with them in the upstairs room in that flat, watching the first flight of Concorde on television. This is a very, very long time ago, and Concorde, the maiden flight of Concorde was on television, and we watched that together in this little flat. We used to walk together round to the University Centre, which was just round the corner, for lunches, and at this time he would hang on to my hand and I would walk him round there, and he was having difficulty now with his hands, and so, like many later assistants, I would have to cut up his lunch for him and feed it to him on a fork, because he was unable to handle that as his disease progressed. We went on holidays together in Switzerland, on the coast of Norfolk, and we did a flight to Malta, where we sat on a beach and watched the waves. This was actually an incredibly cheap flight. It cost £28 to fly from London to Malta and back, including a week at a hotel in Malta. At that point, I had a little cottage in a village called Cottenham, just outside Cambridge, and Stephen, Jane and their children used to come and play with our children. And one time when we were away overseas, they came and stayed in that cottage, because it was a very nice place about 7 miles out from Cambridge in the country. Now, what we were thinking about that time was singularity theorems. The question was there a start to the universe? And this was something that Lemaitre, Eddington, Robertson, all the great cosmologists had been looking at since the 1930s. And in the Robertson-Walker models, if they satisfied the standard models of cosmology, if they satisfied standard physical assumptions, which we would normally assume were correct, then they did have a singularity at the beginning. And so people, Lemaitre particularly, used to talk about the primeval atom and the start to the universe. Now, this is a very big question. Did the universe have a start or not? Incidentally, when Einstein started his static universe model initially, he assumed the universe was unchanging in time. It was taken for granted that there was no evolution of the universe, and it was only discovered much later than Einstein's static model that the universe was evolving and changing in time. Now, these models had a start. Now, the question that we were facing was that because the models were too simple? They're incredibly high symmetries. They're spatially homogeneous and isotropic at every point, and that means they only had 1 degree of freedom. Now, you might very easily think, well, let's throw in a few more degrees of freedom, and maybe these models would have singularities. So could more realistic models avoid the singularities? That's what I was looking at and what he was looking at, and many other people. There was a famous equation called the Ray-Choudhury equation that my friend George Ellis generalized. I won't explain it, which was the key equation in trying to see if there were singularities. And I was looking at these in terms of what are called Bianchi models, spatially homogeneous models, but they're anisotropic, so they have many more degrees of freedom than the Robertson-Walker models. And I had worked in these. I was at this point an expert in those models. And we tried to use those models to prove there was no singularity or to prove that there were, and we couldn't do so because if they were rotating, the centrifugal force could hold the universe apart. As you think of going back towards the singularity, the start of the universe, this centrifugal force could in principle prevent a singularity happening. Vorticity could spin up and avoid it, and that's what the thing that we were trying to solve. Well, in 1965, Stephen and I proved a theorem indirectly that there were in fact singularities in those models, which we published in Physics Letters. Now, this was still a very general, very, very special kind of models that we were looking at. The field was transformed by a huge name in the field, Roger Penrose, who is shown there, who in 1965 published one of the most important papers in general relativity theory. A paper in Physical Review Letters with this diagram you see there. What that is showing is the collapse of matter to form a black hole. And what happens there is as the matter collapses, what he showed that forms what is called a closed-trapped surface. And this is a surface which is very, very strange. The ingoing null rays from there, the area gets smaller and smaller, which is what you always expect. But the outgoing null rays, the area also gets smaller and smaller. And the first person to realize that was Roger Penrose. So this idea of closed trapped surfaces, I'm sorry, I don't have time to explain it more, but we talk about it in some of our relativity courses. This was the key. So Roger Penrose, trying to prove whether at the end of collapse of stars there was a singularity, introduced topological methods, he introduced causality conditions, he introduced energy equalities, the idea of closed trapped surfaces, and the idea of geodesic incompleteness. And what he could prove is that if energy conditions were satisfied, that is, the energy density plus 3 times the pressure is positive, then given causality conditions, there are no closed time-like lines, then there would be incomplete geodesics. What that means is there would be matter which would be unable to continue to live for an infinite length of time. And that means the matter was running into serious problems in that space-time, and we interpreted in this saying there was a singularity, there was an edge to space-time. And that's a really interesting kind of statement. Now, when Roger published those papers, it was a bombshell in the group. We didn't understand the methods, so we organized a whole lot of seminars in Cambridge and with the London group of Bondi and Pirani, and with visitors from overseas, John Wheeler, Charles Misner, and Bob Garoche. And we had a series of meetings amongst ourselves where we developed the methods, and Stephen then started a very, very fundamental series of cosmology theorems where he took Roger's picture there and applied it in a time reverse sense. This is going forwards in time, and he applied it in the reverse direction of time and used it to prove that there would be singularities at the start of the universe, irrespective of how inhomogeneous the geometry was. And these were huge theorems at the time, implying the universe did indeed have a start. He then got together with Roger Penrose and published a final unifying paper in 1970 in the Proceedings of the Royal Society. Stephen and I then got together and showed that the conditions for the theorem are met because of the existence of the cosmic microwave background, and we published this paper showing if you take our point in the universe and follow its past light cone back, it reaches a maximum size and then start contracting in. That means there's a closed trapped surface there, and that happens because of the cosmic microwave background has got sufficient energy to cause the past light cone as a whole to refocus. So we published that paper showing that there was evidence in the universe that there was the time-reversed closed-trapped surface that was required for these theories to be true. I went then to Texas for a while as a postdoc, and we at Austin and the Hawkings came to visit us, and one funny thing happened at the airport. Stephen was now in his wheelchair some of the time. Jane was very, very small. He looked very small. And one of the people at the airport came up to them and said, "Are you unaccompanied children?" We went and picked them up, and I then went with Stephen to Miami to a congress there which took place in the hotel where Goldfinger was filmed. If any of you remember the film Goldfinger, this meeting took place in that hotel, and I presented for Stephen there because at this point he was unable to present himself because his voice was going. We went out for a walk on the beach at this huge hotel, and we didn't realize that the beach got locked at 6 p.m. So we were then locked out on the beach, and we couldn't get back in until we found a way in through the kitchens, where we were treated with great suspicion by the staff until Jane Hawking spoke to them in Spanish, because she was an expert in Spanish, and they were all Cuban, and we were then able to get back in. Stephen spent a lot of time in California with Kip Thorne, his longtime friend, and we flew together from Miami to California. Couldn't get into Los Angeles because of fog, and so I drove us all from San Diego to Los Angeles in a rented car. And incidentally, in that rented car, through the entire drive there was mist and fog, and I couldn't find how to do the windscreen wipers because it was a different system than the one I was used to. And Stephen then moved to West Road, and that's a picture of him with Jane, and he had student helpers to help him here. He was now in this wheelchair. Bernard Carr particularly was a huge help to them, and also went with them to California to look after him while he was there. And this is a picture from in the family, the garden at West Road, with Robert and Lucy running around, and Stephen in his wheelchair and Jane at the back. Now, Stephen and I got together and decided that this theory had reached a stage when it could be summarized in a book, and so we wrote a book called The Large-Scale Structure of Space-Time, in which we talked about all of this. And the question of one of the focuses was there a start of the universe, and I must immediately step back and say we still don't know the answer to that question today, because the energy conditions which go into this theorem, but the density plus 3 times the pressure must be positive, we now have reason to believe that that may not be satisfied. We also don't have a good theorem of quantum gravity, so we still do not know if the universe actually had a beginning. So this is the book, The Large-Scale Structure of the Space-Time, which was known to graduate students as the Yellow Peril. And we did this before the days of word processors. Now you're all used to word processors. You don't know how it is to type the thing on a typewriter, to handwrite the equations. Then you get the proofs, and you have the proofs there from the printing press. You have your typewritten script there. You have to compare line by line, word by word, if what is in the text that they've given you from there is the same as what you sent them. And then you mark the errors, you send it back, you get back a second set of proofs. You again have got to go through the entire manuscript, word by word, in order to see if they've done it right. You do not know what you are missing these days in terms of what we had to do. Okay, Stephen did a lot of other very interesting work. Perturbations in cosmology, he did a very nice paper, which was later on developed by myself, Marco Bruni, Peter Dunsby, Roy Martins. He did work on rotating universes with Barry Collins, and he did work on gravitational radiation, the theory, and how to detect them with Gary Gibbons. His second major theme was black holes. These are key astrophysical objects, as I'm sure you all know. These are objects such that gravity is so strong that light cannot escape, which was indicated in that diagram of Roger Penrose. He devised an area theorem. The surface area of a black hole does not decrease with time, and that means it's like entropy. And so he and others started thinking about whether there could be an idea of gravitational entropy. And this came up then with black hole thermodynamics, 4 laws of black hole thermodynamics. Jacob Bekenstein in Israel was one of the people who started this. And then Stephen, Brandon Carter, and Jim Bardeen wrote a classic paper about the 4 laws of thermodynamics as applied to black holes. And then there was a series of uniqueness theorems for black holes following the work of Werner Israel. Now, Werner Israel was a remarkable South African relativist who went to school in Sea Point and then made his mark overseas, in particular by a black hole uniqueness theorem, which was a very fundamental unique theorem. Stephen showed that a stationary black hole must be static or axisymmetric. Now, how do I get this thing to move? But the biggest thing, his most major discovery, was black hole radiation. He discovered that black hole emit black body radiation due to quantum field theory effects. And the Hawking temperature there, it's inversely proportional to the mass of the object. And this means there's a runaway effect because the black hole is radiating away energy, which means it's radiating mass. as it radiates mass, the temperature is going to go up according to that relation, and so it's going to radiate faster and faster as it radiates more and more, and so there is in the end some kind of endpoint, which is probably an explosion. As many people believe, it may pop out of existence in a massive explosion. It's possible it leaves a residue behind. This is a key important result, which is uniquely his, this idea of Hawking radiation. It was initially rejected by major people in the field. There was a meeting where he was scoffed at for saying that this was the case, but then everybody became convinced that this is indeed true, and this is his unique biggest contribution, which has had thousands of papers written following up based on this work. And if you want to learn about this, I strongly recommend that you get yourself this book, read this book, Black Holes and Time Walks by Kip Thorne. Now, Kip Thorne, as I said, was a close friend of Stephen. They were in Caltech. Stephen went to Moscow and interacted with Russian physicists talking about the black holes. It's described in great detail in this book. Kip Thorne, incidentally, was last year's Nobel Prize winner for gravitational radiation. He's an amazing physicist and a close friend of Stephen. And if you want to read about black holes, this is the book to read. This led to something called the information loss paradox. Is information lost when you throw stuff into a black hole? And Stephen proposed this problem in 1975. And the information, a group of field theorists, people from the quantum field theory side, said no, information cannot be lost. And these include big names like Preskill, Twift, a Nobel Prize winner, Susskind, and so on. And there was a group of them who have written a huge amount saying it's not possible for information to be lost when you throw it into a black hole. That's a big problem, because when you throw stuff into a black hole, it can't get out because the gravity pulls it in. Even light can't get out of a black hole. Radio waves, nothing can get out as far as we're aware. And so saying that information can't get lost causes a big problem. So relativists like Penrose, Bob Walt, Bill Unruh, Ashtekar, and myself say, yes, obviously information gets lost. And there's been a huge debate in this field. Stephen took bets about this, saying, yes, his first paper took it both ways. He then had bets saying, yes, information is lost. Then eventually he said, no, it's not lost. So he's gone backwards and forwards about this. And it's still, to some extent, a controversial area at the present time. It's still not quite clear if information goes in, how it could come out. Personally, I don't think there's a problem. I think information is lost. And the other relativists I mentioned there, Penrose, Walt, Unruh, and Ashtekar, agree with me. Information is lost, and so don't worry about it. One of the major things in cosmology is the inflationary universe and the origin of structure in the universe. And this was Alan Guth's incredibly important discovery. There was a period of extremely rapid exponential expansion in the very early universe. This provides the only theory we have of how the seeds of structure originate in the very early universe. This is a theory whereby we can understand where all of the astronomical structures we see today started from the very early universe. Now, there was a very important workshop, Nuffield Workshop in Cambridge in 1982, organized by Stephen, Gary Gibbons, and Stephen Siklas, where people collectively worked together the theory of structural formation from quantum perturbations, and Stephen played a key role in this. In many ways, this is also one of his very, very important areas, partly because it develops out of his work from the black hole. Okay, his final major work is no boundary condition. So he was thinking about the start of the universe, and he made a new proposal with Jim Hartle based on the idea of the wave function of the universe. Think of the universe as a whole as a quantum object. Then that wave function will be governed by something called the Wheeler-DeWitt equation. And Stephen and Jim Hartle made this very, very interesting idea that there's no boundary. Because initially at the bottom of that diagram, he imagined that time changed from being real to being imaginary. What that means is you change from a space-time with one time dimension and 3 space dimensions to a space with 4 space dimensions. So you change from a purely spatial thing to one with... So time comes into existence at a certain point in the history of the universe, although to talk about the history of the universe is wrong, because down below where it's purely spatial, there isn't any time, so you can't talk about the universe evolving. This is his no boundary condition, initially for space dimensions and time later. Stephen told me this might be his most important work, but it's very speculative and it is not as widely accepted as his other work on black holes. I actually am not sure that this is going to survive the test of time. There are many problems with it. A particular one being, this is fine. The imaginary time trick is fine for an exactly symmetric universe, but once you have perturbations, it's not clear how to do that trick of going to imaginary time. Now, Stephen had many students. Here's a list of them, and I've put arrows to the early ones. Bernard Carr was an important one, Gary Gibbons, Don Page, Malcolm Perry, and so on. And you'll see some of his students had a huge number of students themselves. Gary Gibbons had 45 PhD students. Malcolm Perry had 29. And those are a series of his students. So just like Dennis Sciama had a lot of important students, Stephen had a lot of important students. He wrote the book, A Brief History of Time, which I'm sure you know, the Sunday Times bestseller list for a record-breaking 237 weeks. In this, he describes that no boundary proposal in some detail. I'm not sure that many people who bought the book understood it. But he wrote this book quite consciously because the costs of his medical expenses were going up and up, and he wanted to make money to cover his medical expenses. And this book succeeded beyond his wildest expectations. He got fame and awards: Fellow of the Royal Society, Companion of Honour, Companion of the British Empire, Fellow of the Royal Society of Arts, Lucasian Professor. He had interviews with President Obama, the Pope, and others, life member of the Pontifical Academy, recipient of the Presidential Medal of Freedom, many prizes, the Danny Heinemann Prize, Maxwell Prize, Franklin Medal, Copley Medal, many, many public appearances. And then as his fame spread, he appeared on Star Trek, The Simpsons, Big Bang Theory, and others. And this is symptomatic of this. His fame, he was now an internationally famous person across the world. But you can also see there that his physical condition had hugely deteriorated. What I think is also very important, he wrote a series of children's books with his daughter Lucy Hawking, George's Secret Key to the Universe, and a whole series of other ones, trying to make scientific ideas exciting and interesting to children. And so this is George's Secret Key to the Universe, and Penn South Africa and Pricer, two Cape Town organizations, translated this into isiXhosa and isiZulu. So you can, if you want to, get copies of this book in those two languages. His disease was progressive. He started off walking with a stick. He later used to hold on to my arm. Later, I used to push his wheelchair. And Silver Street had a lot of steps, very steep steps going out. I became an expert at handling those steps. The way you do it is you tilt, you pace the wheelchair backwards up the stairs, you tilt him to 45 degrees and lift him up the stairs, and it works very, very well. He then moved to the motorized chair, and so this was in early times, and then this is what it looked like later times, and it became very, very difficult for him to communicate despite the computer. What you can see there, initially he had the screen, words scroll through the screen, and then he has to click on them when the right word is there, and he has letters and so on. He used to do this with a little joystick. Later on, as you can see there, he had a tiny little thing there, which on his cheek he had a little a light going onto his cheek and a little mirror, and then it registered on that thing there, and that's how he communicated. It became incredibly difficult. So the last couple of times that I saw him, for him to get out just a sentence of 5 words would take him mainly 10 minutes to get out about 5 words. He had huge courage, humor, and he really enjoyed adventure. So the sun is going to go out, and he has in 14 billion years, and you sit there and act as if everything is fine. He used to sometimes say, he would be driving along and people would come up to him and gawk at him, and he would say to them, "Sometimes people mistake me for Stephen Hawking." And one of his sayings, what makes human beings unique? Some people say it's language or tools, others say it's logical reasoning. They obviously haven't met many humans. He used to love having birthday parties. I went to a couple of these where he had discos. He used to enjoy having fireworks and so on. So this is symbolic of his enjoyment of adventure. He used to have a series of meetings at Great Brampton, a place near Hereford, and that's a picture of myself with him in 2014. These meetings were discussion meetings to discuss aspects of relativity at those times. Films, and this was The Theory of Everything. I'm sure most of you have heard about this, and this wonderful presentation by Eddie Redmayne of Stephen. It was beautifully done, a really, really good representation of how Stephen was in his life. Incidentally, what was very bad in this film was the representation of our research supervisor, Dennis Sharma. He was very badly represented, but Eddie Redmayne did a wonderful representation of how Stephen was. He gave a lot of hope to the disabled, and in particular the London Paralympic Games, when he was on the stage there, gave a speech there, told the world, look up at the stars, not down at your feet, and I'm sure many of you may have seen that. How did Stephen manage to live to the age he did when we all expected him to die at the age of 23, 24, 25? I think it was pure determination, pure will. He had an incredible will and an incredible determination to do what he wanted to do, and I believe that that is what kept him alive. And so he was a great spirit and a wonderful mind, from his wheelchair reaching to understand the stars, not letting being in the wheelchair prevent him from letting his mind roam through all of these possibilities. The future of black holes, the start to the universe, is information lost in black holes, and all of these other things. Thank you.